do the shape, polarity, all that sort of stuff. Let's start with this first one. Xenon F4. Valence electrons. 8 for xenon, there's 4 fluorines in column 7. That's 28 plus 8, that sounds like 36. So we've got a xenon surrounded by 4 fluorines. 2, 4, 6, 8 to form the skeleton, 8 of 36. Now let's do the lone pairs. Okay, the lone pairs, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I need 4 more. I'm going to put them on the center xenon. So I get this sort of structure. There are how many groups around that xenon? You should get 6 groups, so the electronic geometry is octahedral. Because 2 of them are lone pairs, the molecular geometry is square planar. It would be bent if there was only 2 atoms surrounding the center atom. Okay, so the bond angle, since it's a square, has to be 90. I've already drawn it square planar, just by chance, the way I've drawn it out. So now we'll figure out polarity, and you'd want to figure out, okay, does this look symmetric? It's pretty symmetric, and so we would call this non-polar. Non-polar, it's totally symmetric. There's no unequal distribution of electrons. So the next one that was up, the next one was CH2O. Valence electrons, 4 for carbon, there's 2 hydrogens in column 1 and an oxygen in column 6. That's 12. So we got a carbon, 2 hydrogens and an oxygen. 2, 4, 6. The hydrogens can't take any more, so I'm going to go next to the oxygen. So out of 12, I've done 6, 8, 10, 12. Filled it up already. At this point, carbon doesn't have an octet. So I'm going to remove one of these and make a double bond. You can check the formal charges. I forgot to remind you to check the formal charges for the top one. But for both the top and the bottom, the formal charge of all the atoms right now is 0. If there's any of the atoms you want me to do, definitely raise your hand. I'll do those on those. But right now, all the formal charges for everything is 0. So we got good Lewis structure. Now, let's talk about the shape. So, how many groups are around that center carbon? 3, so we call that trigonal planar. There's no lone pairs on that center carbon, so the electronic geometry and molecular geometry have the same name. At that bond angle, since it's a triangle, will be 120. Now, I should draw it trigonal planar. Let me do that. Basically, you'd want to draw it with 120 degree bond angles. There we go. So there's the correct shape as you should draw it. And let's see what's else. Oh, is it polar or non-polar? This would definitely be polar. It's asymmetric. Polar means the same as saying it has a dipole. Means the same as saying it has a dipole moment. Okay. So the next one. The next one was C2H6. C2H6. Valence electrons, 2 carbons in column 4, plus 6 hydrogens in column 1. So that's 14. So we've got C C's with a bunch of H's around it. 1, 2, 3, 4, 5, 6, 7, or 2, 4, 6, 8, 10, 12, 14. I've already used all my electrons just drawing the skeleton. Everything has the octet or what it should have. So the structure is actually done. The formal charge for everything is 0, so it's all good. It's a good structure. Anybody remember the name of this? It's ethane. 2 carbons, so an eth prefix, ethane. All right. Both carbons have 4 groups. So the electronic geometry, what's the name? Yeah, tetrahedral. Molecular geometry would be the same, also tetrahedral because there's no lone pairs around those carbons. Okay, bond angle, 109.5 for tetrahedral. Now let's draw the correct shape. So I recommend just doing 1 carbon at a time. Draw the template. There's 3 hydrogens. And then the second carbon. Three hydrogens, 1 carbon. There's our structure. It can be rotated in space, that's fine. But both carbons have to be tetrahedral. Okay, polar or non-polar? This is non-polar. It's fully symmetric. What's on one side is on the other side. And in fact, if you remember from last time, I said that carbon-hydrogen bonds are pretty much non-polar. So any carbon-hydrogen species, like ethane, propane, butane, would be non-polar. Okay. Oh, was that it? Oh, there's one more. CH3OH. Valence electrons equals 4 for carbon, plus there's 4 hydrogens in column 1, and there's an oxygen, 14. So we've got C with 3 hydrogens and an OH. With the skeleton, I've got 2, 4, 6, 8, 10, a 14 already. The only one that needs to fix the octet is oxygen. And it could take the final 4 electrons to make 14 valence electrons total. Now I have 2 center atoms this time, the carbon and the oxygen. So I have 2 separate answers. Let's do the carbon over here. On the left-hand side, electronic geometry, just like before, tetrahedral. The molecular geometry, same, because there's no lone pairs on the center carbon. Now let's do this side, that oxygen, electronic geometry. Yeah, 4 groups, so it's tetrahedral also. But the molecular geometry is called bent, because there's 2 lone pairs. So it's just like the shape of water. Because they're tetrahedral, the bond angle, though, is the same for both, 109.5. Let's try to draw this craziness. So draw the tetrahedral template for the first carbon, with 3 hydrogens around it, then the oxygen, and just make it somewhat bent looking. So I usually like to draw the tetrahedral first because it's the funkiest looking one. And then do the other part second. Okay, here it is. Is this polar or non-polar? This is definitely polar. It's fully asymmetric. On one side is the oxygen, the other side is the carbon. Okay, any questions about this problem before we go on to the next one? Okay. 1s1. And this is just MO diagrams. So let's try to do this. We're going to do H2 plus 1 first. This comes from an H and an H plus. So for the MO diagram, remember in the center, you put the H2 plus, the molecule. The molecular orbitals will go in the center. On the outsides are the atoms that make that molecule, and they have atomic orbitals. On the y-axis, we're going to put an energy scale. We're also going to write the electron configuration, 1s1, and how many electrons are in this species? Nothing. If you want, you could write 1s0, but there's nothing there. Okay, and then you put the energy levels of those atoms. Okay, same atom, so you're going to put it at the same energy level. That's these two. These are both, though, 1s orbitals. They're both 1s orbitals. Now, every bond has how many parts? 2 is what you need to remember from last time. 2 parts. There's a bonding at low energy and an anti-bonding at high energy. Okay? Now, if you remember, and I'll draw them in so you can see them. Last time we also drew out, here's the atomic orbitals, the 1s orbitals, that make a molecular orbital when it's in phase, or bonding, and a different molecular orbital out of phase, antibonding. So again, you won't have to draw those molecular orbitals, but I'm just drawing them so you can see where things come from. The lowercase is a sigma bond because the bond happens in between the axes, so it's sigma. Comes from a 1s orbital. The top is also sigma because the bond happens through the center. Comes from a 1s, but we have to put a star up here to designate its anti-bonding. So we put this asterisk right up there. Okay, when we do the electrons, the left-hand side has 1 electron, the right-hand side has 0 electrons. So there's only 1 electron to put in the middle. So we would call this what? Para or diamagnetic? Yeah, when there's an unpaired electron, you call it paramagnetic. The bond order, make sure you calculate that. It's the number of electrons in bonding molecular orbitals, 1, minus the number of electrons in anti-bonding molecular orbital, 0. So this will form a half bond, which we can't draw with loose. The bond order is 1/2. Any questions before we move on to the, what was that one? Lithium-2. Okay. Try the lithium-2 now. Same sort of idea. I'm gonna get out a new slide for it though. It'll be a little bit bigger than this. Just FYI for your notes. Lithium-2 comes from 2 lithium atoms. Now let's write out the electron configuration now. This is 1s2, 2s1. 1s2, 2s1. Okay. So again, the atoms go on the outside, the molecule in the middle. We're going to put our energy scale again. Here's the problem though. Notice this is the first example we've done so far in lecture that has a 2s orbital. So now there's 1s electrons that go there. There's electrons that go in the 2s. That means we're going to have 2 separate pictures. We're going to have a picture that looks like this on the top for the 1s. We're going to have an identical picture that looks like this for the 2s. Okay, so it will be 2 separate pictures, 1 for each set of orbitals. Okay, let's try that. So I'm going to put the 1s at a lower energy. How do I know the 2s is higher energy? Because what quantum number? Yeah, the number 2 is bigger than 1. That's the principal quantum number. As the principal quantum number gets larger, the energy is higher. So that's why this one's higher up, because of the 2 versus the 1. I'm going to put the same thing, because it's the same atom on the other side. Okay, now I'm going to treat each separately. So the 1s has a bonding and an anti-bonding, or there's 2 parts of that bond. Okay. The 2s will also have a bonding and an anti-bonding. Every bond has 2 parts. So we're going to have identical diagrams on top of each other. One for the 1s, the identical one for the 2s. Now each orbital will be named a little bit differently. This is a sigma, what do I put down here? 1s, and this is just like the previous one we did for hydrogen, sigma 1s star. What do you think this one we call it? Just put a 2s because it comes from a 2s. And likewise, this is sigma 2s star. The only thing that changes is the subscript. If it was a 7s, you put a 7s subscript down there. Okay? So the subscript just tells you what orbital it's coming from. Otherwise, these should look totally identical. Now let's work on those electrons. It's a 1s2, so 2 electrons there, a 2s1. A 1s2 and a 2s1. Now what I recommend is doing each diagram separately when you fill it up. So for the bottom one, I have a total of 2 on each side, or 4 electrons. 1, 2, third one goes up here, 3, 4. Then you do the top diagram that has only 2, so 1, 2. Okay, there's all my electrons. Okay, let's do para and diamagnetic and all that sort of stuff. What is this, para or diamagnetic? This is diamagnetic because all these are paired here. So I'll write it right here, diamagnetic. Okay, for the bond order. There's a couple ways you could do this. Here's my recommendation. Only do it for the top diagram, and you'll get the same answer if you did it for the entire thing. So I recommend when you have multiple orbitals to do it for the top orbital diagram. There's just a little less math involved. So for the top diagram, the number of electrons in bonding molecular orbitals is what number? 2 from this right here. 2 in bonding. Minus number of electrons in antibonding molecular orbitals. So you get a 0. There's nothing right here. That's going to be 1, single bond. And that is the MO diagram for lithium-2. Any questions on this one? Okay. I have, just to let you know, I'm going to get my demo kind of started here. It'll take a while for me to get to it. Because, well, I have to get to a certain point in lecture, and I have to make this stuff called liquid oxygen. Okay? Okay. And I'll tell you more about it a little bit. I just want to get it started. We're going to have some fun with it later. Let's see. Boom. All right, check. Oh, we only have one more lecture after this. Who knew? Okay. I have office hours as normal tomorrow, and then TAs and I will have office hours during final exam week. So I think your final period is Thursday. So Monday, Tuesday, Wednesday of finals week, there will be normal office hours. Okay? as usual, nothing will be strange about that. What else? What other fun stuff did I need to tell you? Oh, awesome. We got to print out here. Lucky run, number 7. I should have got a special prize because I got 7 and it was a lucky run and it was a 7K. But I did it. But I got this. Boom! First place in my age group. What does that mean? This class is award-winning right now. Does that have anything to do with chemistry? No. But if you guys were really angry and formed a mob, I could probably outrun you. Okay. I want to alert you to this picture in your textbook, and we've already done actually all of these except helium plus here. There's an MO diagram for 4 different molecules, kind of similar to what we've done. This is from your textbook on page 416, if you want to see it more closely. Now, what we haven't done is done the MO diagram for anything that has more than an s orbital, which is what we're about to do. We're about to include a p orbital into this, okay? Into our joy of all joys. So, for the p orbital, get a whole piece of paper for this one. And let's do, as an example, N2. N2, that'll have p orbitals, it'll have the 2p orbital involved. That comes from 2 nitrogens. And this is going to take me a whole page. Okay. The electronic configuration, 1s2, 2s2, 2p3. Say for this nitrogen, 1s2, 2s2, 2p3. All right. So we're going to treat each set of orbitals separately. So there's going to be a 1s picture, a 2s picture. That'll look the same as the lithium example. What's going to be new for us is the 2p picture, okay, or that part of the diagram. So let's go here to the bottom of the page. Well, I guess on the left first, I'll put 1s energy level, then a little bit higher than that a 2s, and then a little bit higher than that a 2p. Why am I drawing 3 lines for the 2p? Because there's 3 p orbitals, 3 atomic orbitals for the p. So I'm going to do that, since it's the same atom, same on the other side. 2p, there's a 2s, and there's 1s. Okay? At the very bottom is the 1s as a bonding and antibonding molecular orbital. Bonding and antibonding. It looks just the same as what we've been doing so far. No change here. There's the sigma 1s and the sigma 1s stop. That's the same. We'll put in the electrons in a little while. How about the 2s? There's a sigma, there's a bonding and antibonding just like before. Put little dashes to beautify this, show where it comes from. So it's a sigma 2s, because we're coming from a 2s, and a sigma 2s star. Okay, so just to zoom in on that part of the picture for now, you can see it. That should look the same. Maybe it's a little uglier, but I'm trying to draw the same thing as what I just did for lithium. Okay, again, we'll put in the electrons in a little bit. So this is nothing new here. Okay, the new stuff comes here with the p orbital. Let me draw out the p orbitals just so you can take a look at, see what they look like and all that. They go in the 3 directions, the x, y, and the z direction. So I'll draw this one. There's the one that comes in and out of the page, and the one that goes left and right. And remember, one side is shaded, so I'll shade one side. And let's do the same for the other side as well. So over here, I'm going to draw the p orbitals. These are the atomic orbitals, remember. Up and down, forward and backwards, and then right and left. Okay? There's our p orbitals. Each one has 3. There's 3 p orbitals. Okay, notice what happens when these two come together. These two right here. Okay, I'm going to bring those two together. Right now, I'll draw them here kind of tiny. Right there. Okay, I'll zoom in on it a little bit more. Okay. Those two right there form what kind of bond? Sigma or pi? A pi bond now, because it happens above and below the center point is where they touch. Above and below. So it's a pi. What's the subscript? 2p star or no star? No star, because this is bonding. Now notice what happens. I'm going to draw another one. I'm going to draw these two, the two middle ones, together now. I'll draw it here to the right. Forward and backward is what this one is. Going in and out of the board. Would that be a sigma or pi? And I'm talking about this one right there. That would be a pi, because notice the center point is right there, and the bond is happening not at the center point. Is that okay? This is a pi. What's the subscript? 2p. Is that okay? So actually it has the same name as this one. These two have the same name. They're the same. One's just vertically oriented, the other one's oriented in and out of the plane of the board. Okay? So these two, I'll draw this in black, have the same energy level. So I'm going to put 2 at the same energy. 2 at the same energy. Okay? Now let me draw the antibonding version of those up here. The antibonding version will look like this, where opposite phases touch. That, and this second one I'm drawing is going in and out of the board, even though that's weird. This would be the pi 2p star. Okay, so when those two are above, each one has a bonding and an anti-bonding part. So now I draw both parts. Now there's one that we haven't looked at. It's the one, these here. We haven't looked at these yet. Let's bring these two together now. We'll look something like this. Okay. Is that a sigma or a pi? That would be a sigma. The touch, the overlap happens between the center points. That one's a sigma. What's the subscript? 2p, because it came from a 2p. It's different than the 2s and the 1s. And so there's only one like that. There's the bonding interaction. And the anti-bonding would be up here. I'll redraw that. The anti-bonding would be sigma 2p star, and it would look like that. Oops. Well, you can't see it. There it is. This right here at the very top. That would be the 2p for nitrogen. I know you haven't seen it before, so it looks weird the first time. Again, you wouldn't have to draw these orbitals that I drew. You wouldn't have to draw these orbitals. I drew them just so you could see where things came from, and so that you would know if it was a sigma or pi, or why two levels are the same and one's somewhere else. So that's why I drew them. But you wouldn't have to draw them for the final. Okay, let's fill in the electrons now to finish the picture. I'm going to zoom out so you can try to see all of it. Do the electrons in purple. It's 1s2, so each 1s has 2. 2s2, so each 2s has 2. and 2p3. Each 2p has 3. 1, 2, 3. 1, 2, 3. Okay? So 1s2, 2s2, 2p3. Let's focus in and do each part of the diagram separately. So we're going to do the 1s first. 1s, there's a total of 4, or 2 on each side. So I'm going to have 1, 2, 3, 4. For the 2s now, same. There's 2 on each side, or a total of 4. So 1, 2, 3, 4. Okay, hopefully that looks the same as what we've already done. Now let's do the 2p. There's 3 on each side, or a total of 6. Watch my pen, since this is going to be the first time you're doing this, to see how it fills. First one goes here, 1. Second one goes here, unpaired. Third one goes here, paired. Fourth one goes here, pairs. And then the fifth one goes up here, because the bottom's full now. The sixth one now has to pair. If there was a seventh, it would go up here and repeat the same pattern. So the seventh would go up here if there was a seventh. Okay, let's look at it again. There's the whole diagram. Now let's answer the 2 common questions, para or diamagnetic. Is this thing para or diamagnetic? This is diamagnetic. Notice everything's paired along the center. Everything's paired. So this is diamagnetic. Onward. Okay. Remember, I recommend you do it just for the top diagram. You'll get the same answer. How many electrons in bonding molecular orbitals? You should see 6. These 3 here are, in the top diagram, all bonding molecular orbitals. No stars. So 6 minus 0. Yeah, antibonding, there's none up here. So this is a triple bond. You could draw this with Lewis. It would look like this. There's N2, triple bond. What? The same answer from Lewis and ML here. Okay. Kind of weird. Let's do another one so you can see a second example. Oxygen. O. Here's oxygen. You're going to do the same thing. You're going to see a similar kind of pattern. There'll be one difference though. Okay? So oxygen is 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. Okay, there's oxygen. Has a 1s, a 2s, and a 2p just like before. So, let's do a 1s, a 2s, and a 2p. And same on the other side, 1s, and 2s, and a 2p. Okay? So you got the same sort of setup as before. 1s is the lowest energy, then comes 2s, then comes 2p. All right. So let's do the 1s and 2s. Again, the same pattern as before. There's a bonding and an antibonding. Low energy and a high energy. Low one is sigma 1s, the higher one is sigma 1s star. For the 2s, same thing. There's a bonding and an antibonding. 2 parts to every bond. Bonding and the antibonding. The bonding is a sigma 2s now, and the antibonding is a sigma 2s star. Okay, before we get to the 2p part, that's our new thing we're adding. Let me show you a picture, and this is on pages 103 and 104 of the reader of the textbook. This is page 419. So I'm going to move this for a moment. We'll come back to it. Here is the picture for nitrogen that we just did a moment ago. This is nitrogen. It should look familiar. Notice in this picture for nitrogen, I didn't draw the 1s orbitals. Anybody have a guess why it's not drawn here? You don't have to draw it actually. They're called blank electrons. Special name for the 1s electrons. 4-letter word, not a curse word. Core electrons. You don't have to draw the core electrons. You only need to draw the valence. I'm drawing the 1s in these pictures just so you can see everything. But you don't need the core electrons, so you don't see the 1s. But it should look exactly like what we drew before. Okay? This is true for lithium. If you look at the periodic table, lithium all the way over to nitrogen. Now, as I go from lithium all the way over to nitrogen, what happens to atomic radius? Goes up or down? From lithium to nitrogen, in that direction. It should be going down. For that reason, there's a different overlap of orbitals, and these energy levels change a little. What we find experimentally for oxygen, fluorine, and neon is a slight difference in the p orbitals. Do you see the difference? The sigma 2p and pi 2p levels flip. The sigma 2p and pi 2p levels flip. Meaning that what you see here is flip. Those two are flipped of this. That's the one difference. Okay? You would have to remember that. So you'll have to remember that for oxygen and higher, in atomic number on the periodic table, sigma 2p is at the bottom. For lithium and higher, it's pi 2p. So the oxygen pattern is 1, 2, 2, 1. The lithium to nitrogen pattern is 2, 1, 2, 1. Okay? You wouldn't know that outside of me telling you, because we're not putting numbers to this. In advanced classes like Chemistry 110, you would put numbers to this and you would see how the levels switch. But we're not doing this numerically, so I'm just telling you that they switch. Okay? You'd have to remember that. Also, let me give you a little hint on here. Notice all the sigma levels only have one line. And all the pi levels have two lines. That's going to be true in any picture that you draw, and that's an easy way to remember the name. If you draw two lines, it's a pi for sure. If you draw a single line, it's a sigma. Okay? So that's just an easy mnemonic sort of way to remember this. Okay, so I'm about to draw this kind of diagram for the oxygen 2p that we're trying to work on right now. Let's do that. Move this to the side. I'll go back to what we were working on. We were here. I'm going to draw a really similar diagram to before, but it's going to be this pattern. 1, 2, 2, 1. Connect the dots. Beautify it. Show where things come from. And now I know with my little mnemonic, a single line is a sigma 2p subscript because it's from the 2p. A double line is a pi subscripted 2p. Double line again, pi 2p. But because it's above the middle, I know this has an asterisk or is an antibonding. And the last one line, it's a sigma, comes from a 2p, but because it's up top, again, as a star or asterisk. Any questions with that? Again, you wouldn't have to, on a final, draw the bottom part. I'm just drawing it for completeness. But you'll see many times in the text and other places they don't draw core electrons. They only draw the valence electrons. Let's fill in the electrons now, since we're talking about them. 1s2, 2s2, 2p4. 1, 2, 3, and paired 4. And same for the other side, 1s2, 2s2, 2p4. 1, 2, 3, 4. Okay. Now let's fill in those electrons. Let me zoom in on the bottom part first. We'll do this. For the 1s, 2 electrons on each side for a total of 4. 1, 2, 3, 4. 2s, 2 electrons on each side, total of 4. 1, 2, 3, 4. Now let's go up to the 2p. 4 electrons on each side, total of 8. 1, 2, now watch how this works. 3, and then unpaired 4, pair, 5, 6, and now I have to go up. 7, unpaired, 8, unpaired. If there was a 9, it would pair with the 7th one. Looking at this, is this para or diamagnetic? Paramagnetic, because these are unpaired right there. So we'd say paramagnetic. Bond order. Again, I recommend doing it only for the top diagram. How many electrons in bonding molecular orbitals? Should see 6. 2, 4, 6. These 3 right here. These 3 pairs right there. 6. Minus how many in antibonding molecular orbitals? You should only see 2. These 2 right there. So what kind of bond is this? It's a double bond. You can do this with Lewis actually. It'll look like this, and you get the same answer, double bond. Only problem with Lewis is, we've got random electrons here, you don't know where they are. The nice thing about MO theory, you know exactly where the extra electrons are in all those lone pairs. So, we get more specifics, which will help you for advanced chemistry. When you know where electrons are, you know what the chemistry is. Alright, I think because your mind is about to explode, this is a good time to take a break. Take a break for a moment, and we'll resume in a few minutes.